We could do watching and finish the key.
It's gonna be funny or serious.
Well, actually, I have other plans. I didn't know about it until like literally this morning.
I made like a teriyaki.
You made it? It's good?
I don't know how to try it.
Oh, it's marinating? Like overnight?
Ah, my toothpick is not in the camera, so I can How do you feel? I'm refreshed. I feel tired by the end of the day, all right. Just getting up and tired immediately. So today we have a meeting with lucky number 13. So who we are and what are our goals? What are we doing here?
Learning perturbation theory.
Yes. Why?
Because sometimes solving problems exact is impossible. So we solve a solvable one and then we add some perturbation to make it more realistic.
I don't know what they're doing here, you know everything. So, which perturbation theory are we dealing with right now?
Second order perturbation.
No, time dependent.
Time.
Huh?
Time dependent.
Yes. So when do we need time-dependent perturbation theory? Huh?
All the time.
No. One can, like, if you need to derive van der Waals corrections or amplitude energies, you do not need time dependence. So, which kind of problems request for time-dependent perturbation theory?
Time dependent.
Ah,
Auto-integral interaction.
okay.
Time dependent external field.
Good. Very general, yes, yes. So, yeah, you don't need to be a physicist or chemist or like scientist to answer this question. It's enough to be good in linguistics. when do you need time-dependent perturbation theory when everything is time-dependent? Okay, so when we deal with quantum theory, we like so much the Hamiltonian because it enters Schrödinger equations that we can solve and predict observables. And until our last meeting in class, or 2 meetings before in class, we assume that Hamiltonian is time independent. Therefore, it can be diagonalized, right? It is basically how we solve Schrödinger equation. No? Good. But sometimes circumstances change, and Hamiltonian also changes, and therefore we need tools to address it. So photon-induced chemical reactions is really hard. I'm not sure if it can be ever brought to a theoretical class, because you have simultaneous evolution of light, which is time-dependent electric field, electronic state, and nuclear degree of freedom. So it is like top of the cream that probably not for the class. Maybe at very last meeting. But when the Hamiltonian becomes time-dependent, examples. We already discussed it. Like we did consider one of you, no, 2 of you, taught something about fine splitting and Zeeman effect when system with spin gets splitting of degenerate levels, right? And in magnetic effects, you can either apply magnetic field static that will split them, or you can change it continuously or harmonically that will induce the magnetic moment to follow the field, oscillate or rotate, right? Which is, Brandon knows, when you apply constant magnetic field and then changing magnetic field at given frequency. Which experiment is it?
NMR?
Yep. And everything with just our eye, when we recognize colors, it means we experience time-dependent Hamiltonian. So photons, which are oscillating at the field, fall into our eye and then induce photochemical reactions or whatever. Photoelectric electrons go to our brain and we see all these nice pictures. So what? What do we need?
Hamiltonian.
Yes, we need the Hamiltonian, and we already have it. We just one can write thousands of different brands of time-dependent Hamiltonians, but the simplest one and most practical is when the Hamiltonian changes harmonically in oscillating fashion, sine, cosine. So there is something that oscillates. And what is our goal? What is our not big goal, but practical goal? What are we going to get? What do we need? Well, if you think a little from the bird's eye, everything we do in quantum classes, if you forget about statistics, but statistics also do, we need to predict
Some of the
observables. And in order to predict observables, we may want to have either density or wave function. So we need to predict wave function at a given time. We can assume that if the Hamiltonian is time dependent, then wave function will be time dependent too, and then we will be able to predict time dependent observables, right? So when we were considering time-independent perturbation theory, we were dealing with energies and corrections to wave functions for eigenstates. Now we are departing from eigenstates. If the Hamiltonian is changing in time, we can consider that there are eigenstates for a very short time, but it is much easier to think that we are departing from eigenstates. We are going to consider superpositions of eigenstates with the proportionality coefficients, weights of the eigenstates in the actual state are changing in time, right? So we know how to obtain observable from wave function. And we get a new concept of what we are looking for. We are looking for time-dependent expansion coefficients. So basically, we need to assume a very general form of time-dependent Hamiltonian. And then our goal is to see how the time dependence in Hamiltonian result in change of the expansion coefficients of the wave function. Okay? So we are on the same page. And we did a big leap through, big jump when we met last time. But it was so long time ago. We drank so much since then. So you may have forgotten where did we stop. I can, well, it would be not smart to redirect. You can just watch the recordings. But the tools, so CHEM767 is our tool. What is our tool? Right now, we are going to make a very little philosophical effort. For practical reasons, we don't need to discuss it, because the answer is so simple that you will forget about the relations as soon as you see it. Or if you were reading textbooks forward, you may laugh in silence, like, oh, he's telling you it's just 1 minute equation to write it, to discuss it. So our tool is to make connection. That if the Hamiltonian is changed in respect to unperturbed Hamiltonian, with auxiliary parameter lambda changing from 0 to 1, explaining transition from ideal world to real world, then we can expand our coefficients in series. Just power 0, power 1. And when we plug in this general solution into time-dependent Schrödinger equation, we have already gotten the answers for time-dependent expansion coefficients, right? Nothing new. We stopped, not here, we stopped like half an hour after this idea. So we, 1, 2, 3. When 1 and 2 and 3 are plugged into time-dependent Schrödinger equation, we are getting an answer for approximate answer for expansion coefficients. Plus, we need to assume some reasonable initial condition. Which observable should we look at? I know that as a growing thinkers, we need to think in abstract form, but it is so much easier to target some specific example. So what could be our observable, and what kind of experiment should we probably think about? Well, I will say something not necessarily right, but it will just give a way, a pattern to think about. If we do have a simple molecule or simple object that is spectroscopically active, and we start exciting it with very low intensity light at a given frequency that would allow to excite it. Then, if you think statistically, then small fraction of these objects in an ensemble will be excited, another bigger fraction will be not excited. If you think quantum mechanically only about isolated molecule, there will be growing probability that the system is promoted from ground to excited. And if you suddenly stop exciting, put it in a dark room, there is a chance that the system will emit a quantum back. The longer we were exciting, the higher the probability that we have promoted system into excited state, the stronger will be intensity of the photoluminescence. So, and this can be correlated to the population of excited state. So one of the observables that we can keep in mind is population of an excited state, right? Which will be just probability if you know the excited state. I do not put the number here. So if you just look on the occupation of a specific excited state as function of time, it means how strong will be emission from the state if you stop exciting, put in a dark room, and make a counter of photons to measure this experiment. So we are deriving equations for expansion coefficient, but we are targeting primarily the population. So whatever you will find here will be then taken absolute value square for analysis. So when we spend some time here, we will find that you'll see that the states that were unoccupied will get wave function growing linearly. So it is not the answer. I'm just giving heads up what we are going to get. So we are going to come with an answer, seeing that if the system is continuously excited by low intensity light, the wave function expansion coefficients for unoccupied states will start growing linearly with some coefficient that we will derive. And then the occupation will grow quadratically. So it is qualitatively what we are going to get, and this simple answer is why we are going to sacrifice hours of derivations, or maybe minutes if you are lucky. Any questions about the goals? Because if you are uncomfortable or if you think that it is too narrow, let's discuss now. Because in a couple of minutes we will call mathematicians inside ourselves, and we will just start deriving boring equations.
So for Sergei Tretiak's code for non-adiabatic excited molecular dynamics, is that a perturbation type code? Because to get the population, we do the expansion coefficients just like you shown. But they don't do like C of lambda, all the other terms. They just get the one term. Does that?
No. Why no? The perturbation means that we apply small, something small. There it is not small, and there the problem is the same. And we were overviewing when we met last time that the problem of solving, propagating time-dependent Schrödinger equation forward in time for specific initial conditions can be solved by several other methods, like evolution operator and so forth. Evolution operator is absolutely correct, but it is not practical for big systems or even for moderate systems. The approximation in the method you are asking, non-adiabatic dynamics, when ions and electronic states are changing simultaneously, there is a surface hopping method where occupations of states jump instantaneously from 0 to 1 or from 1 to 0, which cannot be considered as a perturbation.
So Ehrenfest is more. But okay.
And another thing that there one is looking for simultaneous motion of electronic and nuclear degrees of freedom. It is interesting, it is practically applicable, but it is too much for the class. Now we assume all atoms are frozen. We are looking only on electronic degrees of freedom. Or if we would apply, if in class we would apply time-dependent perturbation theory to nuclear degrees of freedom, then we would assume that electronic states are frozen, nuclear degrees of freedom are quantized, and we exploring transitions between quantized state of harmonic oscillator. Okay? So the question you're asking is like another universe, very far more complicated. So at the end of our derivations, we will get an answer for time-dependent expansion coefficients. Ck of t. We will try to recall an expression where we stopped last time, or maybe just one or two equations were compared to where we stopped. So it will be the equation of motion for expansion coefficient. And in between, we need to carefully look onto several aspects. We want to double check that we haven't made an error with phase accumulation. And we'll better look at it once again. Just for curiosity, we may make a comment of connection to pictures. Schroedinger picture versus Heisenberg picture. Then we will assume explicit form perturbation in harmonic form, like sine or cosine, and then we will do apply Euler formula, do integration, and then we will consider resonance condition. Resonance condition. So it is a kind of sketch what we should do. So we are not considering second and higher order perturbations. First order keeps us busy for a time. And it is more thinking than deriving, or more talking than deriving. We can easily practice this philosophy of perturbation theory and immediately get answers for second, third order. They are much easier to derive for time dependent. But right now we better get feelings of how to apply the first order and what are the benefits of it. If we get through it, then and there will be time we can get into higher orders and applications of perturbation theory, but this is a minimum. And I hope we will go through these points today. And when we meet next time, first thing we will do, we will make immediate connection between first order perturbation theory and Fermi's golden rule, which is just a reformulation of the answers that we will get today. Number 0 here is review, which we have already done. Administrative. So March 1st, Wednesday, we will do a brief lab where we will compare exact numerical solution with perturbation solution for some simple object. When we meet on March 2nd, we will start from Fermi's golden rule. And we need to discuss the big free of classes in 2 weeks from now, at the time of American Physical Society, once some people in the class, including me, will be absent. And either before or after, we will need to make presentations number 3 on applications of time-dependent perturbation theory.
I thought APS was doing spring break.
Yes. Is it in 2 weeks?
Yeah, but then then it doesn't matter about APS, because we don't have class anyways.
Margin of classes is bigger, but okay, I'll write here break. We will need to decide, do we have enough enthusiasm to do it before the break or after the break? Okay. So, we did practice the philosophy of the time-dependent perturbation theory, and we stopped at the first order correction. So we stopped few steps after this one. And I have a suspicion that there was one typo or error due to lack of attention when we went after this equation. But today we will avoid and we'll go very carefully. So what do we see here? And before we go forward, Are there any questions? What is it and where did it came from?
Is EK not a function of t, or is it times t?
Times t. Times t. No, we assume that energies energies and wave functions of zeroth order originate from unperturbed Hamiltonian. Unperturbed. When we solve time-independent Schrödinger equation with unperturbed Hamiltonian, I just swapped the order. We are getting zeroth order wave functions and energy. And now we consume them as components of our cooking reaction. So this one typically it is time independent, and typically it is either 0 or 1 or whatever we select initial conditions. Zeroth order expansion coefficient. This one is first order correction. This is our time dependent Hamiltonian. Those are zeroth order time-independent components of wave function, basis functions originating from time-independent Schrödinger equation, and those are energies that also come from here. So we are finding matrix element perturbation in basis of unperturbed wave functions. Right? Where this equation comes from? I don't want to rederive it, but I want to make sure that each of us can rederive it if necessary. Any ideas? So if let's recall what we were doing. If we plug expansions into time-dependent Schrödinger equation, establish equality between expansion coefficients of the same powers of lambda, and then remove wave functions by multiplying by bra from the left, we are getting equation for expansion coefficients, right? And then we do we call mathematicians inside us and do a little math. So what is interesting about this equation? Or what else we should be looking at? So this is an object that converts initial into final. And this proportion of conversion is time dependent. It changes at each time. So in order to find this correction, we need to integrate here. And what else? What else? We do have phase factors. Why? Why do we have phase factors?
Because the perturbation could destructively or it could interfere constructively or destructively.
This is a later consequence.
So this
If
one
yep.
is time dependent.
when we do not have any perturbations, when we solve time-dependent Schrödinger equation with constant Hamiltonian, our solution is that wave function, even if it is in the eigenstate, has spatial or whatever degrees of time independent degrees of freedom are times time component. And if it is eigenstate, this time component looks exactly this way. So each eigenstate with time accumulates phase factor. So it also, the absolute value stays the same because imaginary exponential absolute value square is 1, but it rotates in a complex plane, and then it may result in constructive or destructive interference. But the dimension of this phase is energy times t divided by Planck constant, which is also energy times t, so dimensionless, just quantum phase. As you move, as I move, I accumulate phase. And it appeared naturally because we were acting by unperturbed Hamiltonian two-wave function, and because we used the explicit form with this time dependent in the expansion coefficients, in the expansion form of wave function. What are the indices in this phase factor? Same as indices of the expansion coefficients. K here and V. So they are different on the left and right. So we need carefully migrate this phase factor from left to the right by dividing both parts on this factor. Right? Multiply e to the power plus minus I over h bar times t, then in brackets e0 m, and when we divide, it means we flip the sign in front of the power of exponential. Are there any changes in this equation compared to the top one? No, we did just algebra. So how do we treat, how do we analyze what we have? That perturbation, which is time dependent, is multiplied by accumulation of phase, which depends on the energy difference between pair of states that contribute to this transition between initial and final state. So if we look for perturbation, how the state number n affects state number k, in addition to influence of Hamiltonian, we have also the factor of their energy difference. It's just technicality. And then when we make next step, it will, as Levi mentioned, probably because of looking for it in textbooks or just guessing, there will be either constructive or destructive interference. So all of this perturbation theory is primarily designed for Hamiltonians that change in time oscillating as sines or cosines. And then if the frequency of oscillations of Hamiltonian and frequency of phase oscillations match, the time dependence will become much simpler, especially in the case of destructive interference of these two oscillations. They may cancel each other and get nearly constant term. Okay? These probably I need to write it down, because the rest are technicalities and applications. So the well, I wouldn't say destructive interference, just mathematical cancellations of rotations from perturbation and this phase factor will result in substantial simplification of the final answer. If you see here, we will get just linear growth this time. So they will compensate each other. Good. A little note that is not directly applicable right now, but it is a good time to prepare for the future. So when we are looking for time-dependent expectation value, I'm going to say what all of you already know, but it is a good time for reminder. So we have some arbitrary operator A. And if there is superposition of summation, there will be summation of terms like this. But assuming that we are looking only for elementary contribution to time-dependent observable, there will be three components: bra from the left, quantum operator, and cat from right. So the result does not depend on basis or so-called picture. So we can interpret this writing down where we have time-independent degrees of freedom, expansion coefficient, and accumulation of phase. And here we have conjugation, and phase accumulates in a different direction. Time goes backwards. When you change sign here, it means like we are moving back to the past. So we can tell that this combination of time-independent wave function, expansion coefficient, and phase accumulation is a wave function, and this letter A is operator. And this can be called Schroedinger picture. But nothing will change if we just redefine, if you make a redefinition. Let's consider that time-independent orbital, wave function, and expansion coefficients are considered as a wave function, and the quantum operator times all these non-trivial phase accumulation will be called operator. So we will just move into system of coordinates that rotates, multidimensional system of coordinates in this Hilbert space that rotates according to this accumulation of phase. And this is operator. Okay. And you will call it Heisenberg picture. I'm not deriving any conclusions, but it is a good time to remind about it. The result of perturbation theory can be formulated in either one of those, but in many cases, Heisenberg or its extension interaction picture can be much simpler and useful because we leave out quick oscillations and look only in what non-trivial dynamics in the system. So where are we now? So we've done with equation of motion, done with phase accumulation, and with Heisenberg. So now we need to go with explicit form of the Hamiltonian. So we irradiate system with a quantum, it promotes from ground to excited state, and we are looking into interaction Hamiltonian. So the light is time oscillating electric field. There is both electric and magnetic component, but contribution to Hamiltonian is much stronger from electric field. Let's do color graphic as a difference. So electric field that depends on time, right? So it is not everything, but it is the leading term in the interaction of light to matter. So dipole is just product of charge by position in space. So we always can find matrix element, and I cannot do this color graphic twice. This electric field is amplitude times, let's say, cosine or sine of some big frequency. Right? So we are going to inspect how the harmonically oscillating perturbation to the Hamiltonian will affect will change the population of the states, of the basis states. So we are going to plug in these values into this equation. And here we also need to integrate, just remove derivative symbol here, put in integration symbol there, and go for it. Right? We can also assume that there are much more states, but we have initial state n that is occupied and final state k that we are looking for occupation being created upon further excitation. Then we can set up initial condition. And if we take this initial condition, then the summation will disappear. And nothing will change philosophically, but it will be few symbols less to write down. So we will need the matrix element. We do see matrix element of the perturbation to the Hamiltonian. We see that the only dipole moment is a quantum operator, and the rest are just functions. And if you do want, we can save our calligraphic effort and call it just by matrix element M and K. What else should we do in order to apply perturbation theory and find the change of expansion coefficients? We need to look on the time-dependent part how it multiplies the phase accumulation, see if you can expand or shrink or process it, and then integrate. And then combine everything together. So we are going to evaluate cosine over t times e minus I over h over t. So we set up exclusive form of Hamiltonian, and for the cosine omega t we can recall what? Euler equation. So since we see exponential, imaginary exponential here, why don't we represent cosine in the same form? E minus I h power. Let's simplify our life once again. Let's denote this E n minus E k over h bar. So the dimension will be frequency. So let's call it omega np. Which will be offset of the values, right? So minus I t k plus exponential plus I. Here we have capital omega because we are dealing with perturbation that comes from the light. This one comes from light. And here you have the part from the accumulation of phase in the node. And we can open brackets and write down this half, and then there will be two exponentials. So in the first we have plus sign, in the second we have minus sign for the Euler equation. Two exponentials with different signs in the power. So this came from here, minus and minus. And the second term came from here. Minus times minus will be plus. And there was a second term. Omega k plus omega k. Whew. So where are we now and what we are doing? We are pursuing to find perturbation to expansion coefficient for each state. And we know that when we pursue the expression, the differential equation for this expansion coefficient, the coefficient in this differential equation is a product of matrix element of time-dependent Hamiltonian times phase accumulation. We took this term without constants up front and found its time dependence. How does it depend on time? Right? And we are going to plug it into this differential equation and solve, which will be simply integration of this function. So we will be just integrating exponential. Make sense? What are we going to get while integrating? Whatever is by the power of exponential will drop into the denominator and we will see resonance condition. So we need just to make it carefully, but we are going to get that perturbation will have some non-negligible consequences only in case when frequency of incident perturbation coincide with energy difference of the levels that it affects, right? So we are going to do this technical machinery, but we are going to get just resonance conditions in whatever, in a short time. So I'm plugging everything that we developed into this solution. So it will be integration. Now we need to plug in the matrix element, which will be minus u k. Vector times amplitude of electric field oscillations times 1/2 over NP minus capital omega plus so originally we did have the C sub 0 k and summation over k here, but since we agreed on the initial conditions, we are removing these two terms, because we will have only state number k initially occupied, or state number n initially occupied, and all other states will have influence from the initial occupation of state k, of initial state. What do we do next?
Separate and integrate.
Separate? What to separate?
Sounds.
Oh, okay. Right.
Oh no. At least you already told me the answer, so it's good enough.
So, what Levi is doing right now is taking the no.
No. Isn't this just constants?
those are constants. You're correct. But there are. Yes. So Levi took the integral of exponential with indefinite value of integration variable, but it is a definite integral where we should follow specific limits. So from initial time to final time. Suppose that we switched on the external perturbation at time 0 and we stop it at time t. And we see what are consequences. So we switch here to ignition on at t equals 0, switch off at t, let's see, t prime equals 0. You're frozen.
So this part is
You can put t prime equals 0 and continue just the numerator.
Just put -1 in the numerator, right?
Yeah.
Good.
in that case.
The -1 has to be over though. Yeah, because the second part's gonna be 1 over the denominator. Then you subtract it out. Whatever distributed across. It's like, I'm saying.
And exponential.
He's doing 2 steps. Oh, I see.
Because you have two different.
Okay, yeah, thank you. Or you want to continue cleaning it up? I think you can ask Brendan to just, you are giving good advices. Just clean it up and see.
Clean it up, okay.
Yeah, maybe factors up front.
The factors up front, I was gonna put this as denominator here. That.
No, I mean this matrix element of.
Oh, I see. Because this goes.
Just make bigger brackets at the left and right and put all everything we need.
So I can do.
Yes?
That.
Yes.
And move this stuff up front.
No. The signs are different here.
Oh, yeah.
Just repeat what is
Okay.
what is here.
Yeah.
Good, yeah, thank you. Unfair?
Why didn't you choose right in the first place?
No, no.
We are
I just made it bigger because I didn't want to write all those terms.
we are almost there. We're almost there. We can probably cancel imaginary unit.
Yeah.
Right? We can
But
probably what I'm going to do is to make a screenshot of this board and then erase everything except last equation. Because we need maybe 2 lines more and then we will be done.
sweet. Are you being lazy, not just that?
one every I don't know, 2 hours before.
It's only an hour and 10 minutes right
So I'm erasing everything except equation written, integrated by Leray, plugged in for definite limits by Jagged, and cleaned up by Brennan.
now. I feel like we could have done that in one step.
Why don't we take the denominator, swap it underneath? Make
So it is Leray, Jagged, different equation.
L shape.
Maybe we should make it functional. LJG.
It's FGB or L.
Oh wait, no, it would have to
Yes.
be.
This is
No.
now first name, last name.
No, Lightstrom.
Well, but he
Like-
said Levi.
Yeah, but L doesn't have to either.
Well, yes, it's a degenerate.
Yeah.
I can't handle you guys right now. So Simon, take those, swap them, and then.
So how does this equation look like if you plot it?
At the 2 points where omega is equal to.
Let's assume that T is very big.
It will feel like a peak where omega at the resonance condition where omega and k.
Just draw dependence of this expression on the omega at very big time. Or absolute value of this. Uh-huh.
This
One,
function of omega.
The omega capital. Because we have small omega sub nk as input about our molecular system. And omega capital is,
well, this.
we need to ask experimentalists, a knob in front of spectrophotometer, or maybe nowadays just computerized way to change the frequency because you turn on the prism or diffractional. How do we correctly say, how do we change omega capital in the spectroscopic experiment?
Depends on the source. Some sources have, you can change it. Sources I don't, they're already set. But yeah, there is like a monochromator that you can
Okay,
use.
yeah, rotating monochromator and focusing on the right part of the spectrum.
Wouldn't you just have? So this would be.
This also has a time.
But let's assume that time goes to infinity.
Oh.
So this function also depends on omega.
So
And just sketch. It's not for the record, not for the grade, just general expectations of this equation. So we know that absolute value square of any exponentials, of imaginary exponential, is 1. So there will be some oscillations, but this is about 1, this is about 1. So the nominator will be never.
What about when WNK is equal to negative omega?
Good. Thank you.
is that what
Yes.
So that's this case, right? When these are equal, this stops.
Well, when these are equal, this doesn't die. This goes to
Yeah,
a
this-
big number.
Yeah, this goes to 0, then that means it goes to infinity, so then you have,
Or if we take absolute value.
then you just
Okay, yep, very good, very good. Thank you. So this equation gives two cases. So because of the difference of incident frequency and frequency of transition between levels in the denominator, this will give the change in the occupation in the population of excited state will be achieved only if the frequency is equal to the incident light. It's only is equal to minus omega n. If it is off resonance, so we can call it resonance. If it is off resonance, then perturbation will be negligible and system will be not excited. If you know that there is a molecule with only two active states that absorb, if it is not like quantum dot which absorbs everywhere, but molecule with fixed levels, only few levels, like 2 levels in the range of our where we can access it, then we tune and it will not absorb at higher or lower frequency, only at resonance condition. Okay? So if we have this case, it means we use only the first term and second term neglects, right? If you know for sure that our frequency of incident light is positive. So then, let me see, first order correction, T equals U in times field square E is T. Are we happy with this answer? Or is still non-digestible for pleasure? Can we simplify it for analysis? So here we set up a limit that time goes to infinity to get a logical analysis that resonance condition is important. Now let's look onto the limit time is approximately 0. So we know that on the long time scale, we need only resonance conditions. But we know that, well, we do not know, but let's try to do at least something. The limit when we are just after, very short instant of time after we applied external perturbation, and we see initial steps of change in the occupations of levels, in the expansion coefficients. What can we do here? To make it more simple and pleasant and get our answer of linear growth. E to the power x. Who was not here?
that's x plus 1 over x.
What was that?
I think it's x plus 1 over x, and then there's more terms, but then they die off quickly. I think.
Let's check. Let's check.
Let's check
So
Wikipedia.
E equals approximately 2.7, right? Yeah. If we do e to the power 0, it should be equal 1. We plug 0 into here, and we go 0 plus
No, that
infinity.
won't work. I guess I was doing a Taylor expansion. Whoopsies. So it's just 0. I mean,
So the Taylor expansion is is 0 plus equals 0 times x plus 1 plus we do not care. It will be x squared over 2. These two terms are sufficient. Now, it's not the end of the term. Now, our x here, x equals minus I t omega and k minus omega. Can you use these two pieces of knowledge and rewrite this expression? So you rewrite everything in the same form as it was before, except the exponential that you found. Everything that was in the power of exponential just add -1 because it was originally here. Yes. Good. Close. Yeah, close the graph. Thank you. Sam did hard work, and now I will take the cream. So, look here. Great intellectual breakthrough. Two units cancel each other. Right? Second intellectual breakthrough. Okay, so the resonance condition cancel each other. And then we get first order correction, k of t approximately equals matrix element of transition dipole times electric field two constants, and here we have minus I times t. That's it. T minus I t. alpha times t, where alpha equals minus I k times electric field. Right? How do we interpret it? So all levels that were initially unoccupied, so their expansion coefficients were equal 0 at initial time, are gaining increment, linear in time, with the pace proportional to product of matrix element of transition dipoles times strength of electric field. Of course, when we go further in time, it will be something different, but on a short time, this will be applicable also on a longer time scales if the intensity or the strength of electric field is negligibly small. So if we look on a very non-intense light source, then this solution will be applicable. Can we consolidate things together? So C, K, not equal N. So all states that were originally unoccupied are getting, oh, it is already here. Let's look on the occupation. C star K times C K will be plus I U E 2H bar T times minus I 2H bar U times E equals I times I gives minus, minus times minus will be plus. So the U, E, scalar product square divided by 4H bar square times T square. So if we look on the occupation of the state number K, at time 0, it is 0, and then it expected to grow quadratically. So at short time or at low intensity of incident field, occupation changes quadratically. At time 0, it almost doesn't change, and then it picks up pace and goes quicker. Any questions? And we did it for arbitrary system. So it doesn't depend on the specifics, whether it is hydrogen atom or quantum dot, or it is also applicable to nuclear magnetic resonance experiments. So it is very general property of perturbation theory. If you look at the low intensity perturbation, harmonic in a resonance, then it will give linear growth of wave function expansion coefficient and the quadratic growth of population. So C, K, no, C K equals C0, K equals C1, K. And then due to initial conditions, first term is 0, and then we need only the first term. We are growth of wave function expansion coefficient, quadratic growth of population. Any questions?
So since the dependence on frequency is removed, does that mean that any wavelength can excite?
Well, we are taking the least action path in our considerations. The equation that you guys direct is general, and you can plug in any values of frequency and time. But for qualitative analysis, we took the limiting cases. The question, by the way, is as follows. What will happen if we lift the resonance condition? Take excitation of a system by off-resonant light. It will still perturb the occupations, but the base, when we take care of these factors, it will be excited also quadratically, but with lower pace. In order, if you want to get maximal population in the excited state, you need to match resonance condition. Make sense? Whew. I think we are done. Meeting with lucky number 13 is complete. We are going off records, and I will stay just in case you have more questions.
We'll have to go back.